to you.
Okay, well, good afternoon, everyone, and thank you for the welcome, and thanks for the request to have a chat with you guys about um, the possibilities of zero Portland cement concrete and the applications to date that we have applied in South Africa. So basically, what we'll be talking about is from grey to green, past, present, and future. Now, what I'm going to want to do is actually change your perspective, because perspective is a very important thing. It is based on knowledge. When you see something, you assume it is correct because that is the knowledge you have. But if you have other knowledge, you can actually see things from a totally different perspective. You can assume things of people that they might have the knowledge or be better off in that. But from a different perspective, you might actually understand a little bit more about this. And then we will going to go into some technologies. A lot of people have said cell phones, everyone's going to become asocial. This technology is going to kill society. Strangely enough, approximately 100 years before this, the exact same thing was said about newspapers. So where technology is driving us forward, it's not always separating us. But when it comes to chemistry, there's a lot of very interesting technologies. And if we apply those technologies properly, we can get some very strange results with some quirks that are quite radical. So as we go through this, you're going to see some things that are weird. I'll put you that way, that do not conform to normal concrete technology. Please understand that the way we apply concrete technology is through a chemical perspective rather than the engineering perspective, which is more on physical forms. So from that, let's jump into what we have done. So portside, something in the backyard of Cape Town. This was a very interesting project. The first building project where we applied larger than 50% slag. The standard mix was a 65% slag with a 35% cement. We did do some of the mixes at 85% slag. We added some stone and some dune sand with a small amount of water, some additive on the side to make a gorgeous looking concrete. Now, this is to date still the highest pump job done in South Africa at 154 meters. The carbon emission reduction on the 60 MPa was approximately 58% and attained an average 88 MPa strength. Slightly slow to come in. The 40 MPa had an average strength of 62 MPa with a 52% reduction in carbon emission. Now, this carbon emission reduction is in comparison to the same strength material from a ready-mix supplier. Now, as you can see, the 30 and 40 had the same strength. That was because the 30 MPa was achieving these strengths that the 40 MPa got melded into it. All of this testing was done by independent tester, and the testing was actually done between Lafarge and UCT with Professor Hans Bersenhausen. The 15 MPa even had a reduction in carbon emissions with quite a high 28-day strengths. As you can see, as we went to the higher replacements, we applied a bit more safety factor, and yes, we did overachieve on the strength. Next one that we're going to look at was a year later at the City Deep Container Terminal. This was the first application of zero cement concrete in South Africa. So this concrete was tested at Beton Lab, and the shrinkage result was 0.022. As we all know, that the shrinkage below 0.05 is considered good concrete and good concrete practice, and your normal shrinkages are between 0.035 to 0.05. A 0.022, as tested by Beton Lab, is actually a very good result. This is a picture of the first slab cast commercially of zero cement concrete. This is a picture of Pierre van Vieren of Marion Roberts. I think he was very excited that after 3 days, the concrete had actually set with no cementing. But it didn't stop there. The strengths have kept climbing. 51 MPa at 28 days, 70 MPa at a year, 75 MPa at 2 years, 78 MPa at 3 years. The most recent test done at 8 years has shown an 85 MPa. So strengths are continuing to increase. What might have made Pierre a little bit more excited was a 30% reduction in material costs and a 25% reduction in labor. Now, right in the middle there, you can actually see the zero cement or zero Portland cement concrete. Still has its broom finish, and this picture was taken approximately a year after the construction. So, or not a year after construction, sorry, a year after handover. So the broom finish is still on the concrete, with the concrete next to it having lost its broom finish. Just by the way, the concrete next to it was also a high volume fly ash concrete of approximately 68 to 70% fly ash. The average strength was about 55 MPa at 28 days. And at 1 year, the high volume fly ash concrete achieved 125 MPa. The carbon emission reduction for the 50 MPa was approximately 92.7%. On wind farms, we have applied this in several applications. These things are absolutely ginormous. Now, at Luriesfontein, we were using between 10 to 35 kilograms of Portland cement per cubic meter. We did have mixes that we were also doing at 0 kilograms Portland cement. Now, the carbon emission reduction we got at Luriesfontein was rather high as well, with between 64.2 to 91.5%. So what are we doing now? So there are many toxins and there's recycling happening, but the recycling in concrete is not really something that's on everyone's minds. And we have done certain applications, certain projects where we've increased the amount of fly ash or slag or other types of eco-binder. But the aggregate in water has generally been virgin aggregate and potable water. As you can see on the Gautrain, we use 32 to 45% of a fly ash binder. On port side, we were using 65 to 85% of the slag. Aggregate was virgin, water was potable. Then we started looking at things slightly differently. At the City Deep Container Terminal, we had eco-binder at 68% of fly ash, up to 100% of a blended slag fly ash. The aggregate was virgin again, water potable. So we decided to take it one step further And at Lewis-Fontaine Wind Farm, we had 75 to 100% eco binder. Aggregate was still dug up out the ground, but the water was non-potable. This water had sulfate contents in the region of 15,000 parts per million. Now, generally, you cannot use anything above 3,000 because of sulfate attack. But with a huge amount of testing that was done with PPC, we were able to use this due to the high amount of slag or absolute slag use. Currently, we are doing projects with 80 to 100% eco binder, with 100% waste aggregate, and water that's 100% effluent. So let's have a look at a few of these projects. Now, this is a shotcrete application where the requirement was 40 MPa at 28 days, 1 MPa at an hour. They wanted a blend of wet tailings and binder and a blended material with an open time longer than 1 week and an energy absorption of 900 joules. Now, the blended material with an open time longer than a week, if you generally blend a shotcrete material, it will set in an hour or two, or if you've got fly ash and slag, in 3 to 4 hours. Now, what we have been able to accomplish here is a material that's actually got an open life of up to a year. As long as you continue agitation, this material can sit underground and just wait for the primary and secondary activation. And you've always got material available. The nice thing about it is because you're using pipelines rather than cages, the saving to a mine is absolutely massive. But let's have a look at it. This was the shotcrete applied. As you can see in the top section, the accelerator was not 100% balanced yet, but the application is 75 to 100 mil thick without too much of an issue. So this is a zero cement based binder. The open time when initially mixed is more than 6 months. After activation, you have 1 hour, then you can accelerate it further to have strength in 10 to 30 seconds. What we are experiencing currently is we are getting approximately 1.5 MPa in 3 to 5 seconds. So it's a bit more rapid than we had initially tested. This is what the material looks like when it is crushed. You will see it as a beautiful turquoise color. It goes from a gray material to a turquoise in a hydrate form, and then it polymerizes into a pure white material. Flexural strengths approximately 7 MPa at 7 days and 12 MPa at 28 days. Compressive strengths at 40 MPa at 7 days and 55 MPa at 28 days. The saving on carbon emissions compared to standard shotcretes of approximately 500 kilograms of carbon dioxide per cubic meter. Now, these are shotcretes that meet the same strength category. Not your standard 25 MPa shotcrete, your higher 50 MPa shotcrete at least. But let's have a look at it. This mix has been mixing for 2 hours. So after 2 hours, you can see this is after the first activation. So this will be underground, and as you can see, it is soup. Now, that material is then blasted against the wall, and I know it looks strange because normally shotcrete is almost a plaster consistency. So when it hits the wall, there's some accelerator that helps it with zero rebound and to set. But this absolutely fluid material goes against the steel shutter here with zero rebound, and it actually achieves a 1.5 MPa within that 3 to 5 seconds. Now, this is the strength at 28 days, as tested by Geopractica. So Geopractica did this test, and as you can see in the panel, we are achieving the 40 MPa, and as the deformation gets to 25 millimeter, you are still having 800 joules of energy being absorbed by the shotcrete. Now, this is the most important aspect about shotcrete underground, how it can absorb energy from the earth moving. Now, as you see, with a full 25 millimeter deflection, you still have 800 or in excess of 800 joules being absorbed. We've also applied the zero cement application at chemical plants. This chemical plant, we're not allowed to mention the name, but it produces hydrochloric acid and sodium hydroxide from electrolysis of salt and water. So as we know, hydrochloric acid eats away concrete very quickly. Sodium hydroxide softens concrete and leads to the deterioration of concrete very quickly. So the application here is a zero Portland cement concrete on this entire project. Now, as you can see, the concrete on the right and the bottom here, we have applied the right mold oil. On the left, a normal mold oil, as you normally use with normal concrete, was utilized, and it did not work. When you go to the zero Portland cement systems, there are certain aspects which you have to understand that will change. The concrete itself, you can make very similar to normal concrete, but there are certain aspects about the chemistry that do change. And as such, you cannot use the same mold oils or repair products. You have to relook at what you are doing in these applications. But this concrete is highly resistant against hydrochloric acid and sodium hydroxide, where this is a big weakness in Portland cement concretes. Further to that, we've also applied this in a few precast setups in pipe manufacture as well as elements. And this was already in 2015 that we applied these type of things. Here we have a self-compacting zero cement concrete. As you can see in South Africa, not the most sophisticated methodologies. But as you see the concrete run, you can see it running under the spacer and the stone staying right on top of the concrete with no segregation showing. And there's the concrete meat in itself. So this is what we have done. What we as ARC Innovations are looking at in the future is actually using mushrooms to stabilize roads, and we are looking at using the mushrooms with dump ash from the power stations to actually do the stabilization without the use of cement. So the mushrooms, as you can see, the root network is stunning, and your deviation within 7 days, you already have mushrooms growing with dense network. We're also looking at certain applications for nuclear waste control using the zero cement material. Due to the nature of it being a pseudo-zeolite, it can actually absorb certain radioactive elements and pull them into a crystalline structure and make them inert in that structure. A lot of this work is being done by Dr. John Provis as well as Daniel Easterman, but we are following that, and we are looking at any nuclear builds in the future. We are going to progress with this material as well. So that is basically what we've been applying. The actual costs of the materials, we went through it marginally in the presentation, but the costs generally are very similar to concrete. Depending where you are, it can be 30 to 40% cheaper or 30 to 40% more expensive. Where we applied it in the chemical plant, the price was marginally within 10% of the price of normal Portland cement concrete. So that's it. Let me stop sharing. Now, one other aspect about this is the nature of what's going to be happening shortly. With COP 2026, there are large tax incentives coming into place when you purchase cement. And by the year 2050, you are looking at paying an extra $250 a ton for cement in Europe and an extra $175 a ton for cement in South Africa. That is just in tax. So we need to keep an eye to have a look at these type of materials. It is not there to replace cement. It is just another tool in our belt for different types of applications. Thank you.
Awesome, thanks, Cyril. I just want to first question that I've got is, so this, for all practical purposes, this is just a cement issued to the ready mix companies, or ready mix companies purchase it from a supplier, and then the batching process, everything is I suppose textbook from there, or are there any specific changes or any specific implications on the mixing process, if I can, in a sense of, is it a plug and play system, or?
Well, all the applications, all the large scale applications to date have been from standard concrete plants. So AfriSam have been involved in 2 of the projects of supplying the zero Portland cement concrete, 2 different sites, and then what we do is we add activator when it gets there. So the material basically will sit in the mixing truck forever. It won't set at all until you add those activators.
Cyril, can I ask a question, please? What is for these projects that you mentioned, City Deep, container terminal, and the wind farms? What are your cementitious materials that you used in these mixes?
Well, at City Deep, we used the normal PFA as that you get from Letabo. Now, that was on the high volume fly ash. What we have done in the actual zero Portland cement concrete is a blended material between slag and fly ash. What we have done on other applications, like currently at Medupi and Kendall, we actually only use fly ash with its activators. So the material we'll use generally moves from the fly ashes to the slags. You can use different clays like kaolin or metakaolin, as well as certain mine tailings you are able to use.
And what are these activators that you use, or is that secret?
Well, yeah, it's actually not a secret. You know, at City Deep, we use the Gen 1 stuff, which is not nice at all. Yeah, it is a sodium hydroxide and a sodium silicate. So the unusual thing though is generally with geopolymers or alkali activation, the amount of activators that get utilized is anything from 20 to 32% of your mix. So you're looking at 250 to 320 liters of activator. Now, when you're utilizing that amount of material, it increases your costs significantly. And this is why there's a huge limiting factor in applications that have been done in Australia, in Germany, in Britain, in the US, because they are still going down the route of using yeah, a 18-pound hammer when a small little scalpel will do. Our application at City Deep, we actually only used 4% activator compared to convention, while achieving the 50 MPa at ambient temperature. You'll find a lot of the applications, the people are heating the materials to try and get those strengths. But we are able to do it at ambient temperature or even down to minus 10 degrees with a very small amount of the activator compared to what's normal. So at City Deep, we used 4% of the activator, but that was the Gen 1 material. At Fontaine, we upped the ante a bit, and there we used a Generation 3 product, and the amount we used to activate the slag over there was a 0.4% of activator. So we put in 7 kilograms of activator per cube of concrete to turn on the slag and achieve a 36 MPa at ambient temperature.
Cyril, sorry, another question. Can you go into a bit of the chemistry, how the activator reacts with the cementitious materials in order to produce hardening?
Well, you see, with okay, let me not look at cement. Okay, with this type of chemistry, a lot of it goes about the alkali activation. So when you use a sodium hydroxide, it dissolves the shell of a fly ash particle, and it allows a silicate and an aluminate material like monomers to go into solution. Those monomers then react with each other to form your pseudozeolite. So you're actually forming a polymer by breaking down the material and dissolving it into your water with your high pH. Now, I don't like working with the sodium hydroxide. So what we have done is we have moved to different systems, but with the same principle. So to get the dissolution with the aluminates and the silicates, they dissolve in high pH or low pH generally. But if you look at several applications, like in the human body, in the lungs, lung fluid can actually dissolve silicates. And this is one of the reasons we get silicosis. And that pH is between 7.25 and 7.45. So looking at the actual chemical makeup of lung fluid, you can understand there are certain materials in there that chelate with silicates as well as aluminates and dissolve them without having to go for a high pH or a low pH. So you can actually have neutral salt activation like what we did at Fontaine, where you use a solid material, you can have it in your hand, and you put 7 kilograms in a cubic meter and achieve a 30 MPa concrete without too much of a fuss.
Thanks.
Right, so one or two questions that came through on the chat. The one is, how do these materials perform from a durability perspective, assuming service life? And then the other one that kind of goes hand in hand with it is, what is the premise for the chemical resistant? Why is it chemically resistant? Is it a inherent alkalinity of the material, or is it does it form like a protective shell? How does that work per se?
Okay, on the durability, this is why we've been following City Deep so closely, and we've been doing extensive work on it. We've been running durability testing as well, and the durability testing has shown improvement from 28 days to 1 year to 2 years to 3 years to 8 years. So we have a continuous improvement in durability. So it is getting stronger, it is getting more durable over a time of more exposure to the working environment. Now that is exposed to elements, and it's exposed to all the stresses as per normal. So that's on the durability. On the actual chemical, now it comes back to Erhard's question on the use of alkalis to activate, or acids, or in normal Portland cement, when you are using a normal concrete, if you use Portland cement with little fly ash or slag, you will have a material that's generally known as Portlandite or calcium hydroxide in the pores. If you don't use any fly ash or slag, approximately 22% of your pore space will be taken up by Portlandite, calcium hydroxide. Now, calcium hydroxide is extremely open to attack by acids. One of the biggest problems about Portlandite is it takes up space but gives no strength. So that's why there are several companies that have got to that understanding where they use that Portlandite in reactions to increase the durability in their concretes by adding silicates or something like that. The whole crystal growth, extra waterproofing, etc., craze. Now, if you look at the polymer chemistry, the material, when it has polymerized, does not have the same pH as concrete, where concrete's pH, because of all the hydroxides and things like that, your pH maintains quite high. I mean, this is why it passivates steel so well. This material, its pH in a hard state is much closer to 7. So the attack from both alkali and acid is negligible, as well as a lot of the crystals that are actually formed on the nanoscale. So you have a nanocrystalline form that is highly resistant to chemical attack. I hope that's answered your question in a few ways.
Both of them.
Cyril, I've got another question, please. How sensitive are these concretes to curing practices?
It depends what base material you're using, what base material you are dissolving, and what activators you use. If you look at what's applied now by the majority of people in the world on the zero Portland cement concrete, it's Gen 1. So the hydroxides and silicates, and they add enough to kill the concrete. And if you have exposure to water within the first 24 hours, you are in trouble. Your water comes in and starts removing all the goodies that have dissolved, and you have major efflorescence, and your strengths are not quite there. So to a certain degree, the exposure is crucial for these type of materials, as well as the curing. These type of materials, even if you move away from the Gen 1, the materials that we are playing with now, Generation 5 and Generation 6, you cannot do water curing. They do not do well if they cannot breathe. They need carbon dioxide as part of the polymer. So they breathe in carbon dioxide to polymerize properly. And the water, if you have water there, it actually stops that carbon dioxide going in, and you stop your strength gain. So if you use a curing membrane, your carbon dioxide can still move through without too much of an issue. But if you do water curing, you will compromise your structural integrity of this material.
Okay, so then just to jump on the back of Erard's question, Cyril, what would be the ideal curing method?
To be honest, black plastic. Black to absorb as much sun heat as possible, and plastic just so that you have an enclosed environment. Okay, I saw Donovan's got his hand up.
So then my question then is, in terms of relative humidity, I mean, down here in Durban, we're running between 70 and 90% humidity. How would the humidity affect the curing then, if you've got a high moisture content in the air? Because what I understand is that you want as little water as possible.
Yeah, you want as little water as a film. In the air, it is not a problem. All our zero Portland cement concrete is cured within the curing chamber, just above the water. So your humidity is still 90% plus of your environment. As long as you don't have that layer of water on it, it can still breathe the carbon dioxide and gain strength properly. And in so doing, you can actually cure your concrete faster if you expose it to carbon dioxide as well. You can get what you would normally expect at 28 days within hours. So it is also another route you can look at with the material. Any other questions?
Right, Cyril, just another question, bringing it back to the durability aspect that we spoke around a little bit earlier. Is there an indication, obviously with the pH being slightly different, so will your steel be susceptible to the conventional carbonation and kind of those attacks that go characteristic of aging concrete? And how does this battle long term? Like, have you forecast a 60-year design life, or 100-year design life, or 1,000-year design life? How does it fit into that more, I suppose, conventional view of durability?
Okay, well, there are several issues when it comes to the durability, because one of the aspects, if you look at, let's say, chloride testing, for instance, all the chloride testing for durability is faulty, because it measures via electric current. So anything that is naturally away from a pH 7, the further you away from that pH, the more current gets made, the worse it shows as chloride conductivity. So when you're using materials like slag and that, your electroconductivity diminishes greatly because you're moving away from your high pHs with your cement alone. That's why with fly ash, you also diminish, but with your high amounts of slag being used, it gives you the best chloride conductivity results. But if you actually look at the test methodology, it does not measure the actual movement of the chloride particle. It measures an estimated movement. And this is why, with a lot of work done by Tom Robinson at University of Honolulu, he has shown that the chloride conductivity tests, every single one is actually null and void. The proper test is actually to take the material and measure chloride in a fixed material. So it's difficult to say, yes, durability, carbonation, and chloride conductivity and all these things, when there are actually, unfortunately, a few questions still up on the durabilities. But with carbonation, because this material actually consumes carbon dioxide to form your wall of polymer, and this material, when you're using alkali activation, yes, your pH will be high and you will have a similar durability or passivation to normal concrete. If you use neutral salt activation, your pH may only hover in the region of 9.8 to 10.6. So it's almost on the cusp of the steel passivation. So these things definitely need to be kept at the top of the mind when you're doing these designs. So if you're using fibers, for instance, macrofibers, okay, no problem. You don't have to worry about passivation. But when you start using things in a structural aspect, you need to start reviewing what you are doing and if your passivation is high enough and how that movement of carbon dioxide is going to affect your pH. Has that answered your question, Billy?
So, sort of. I think to some degree what I'm after is a forecast service life, or if you have an idea of will it perform similar to concrete with a 40-year design life or 60 years? Is it slightly shorter? Is it incredibly longer?
To be honest with you, a lot of the models are theoretical. A lot of the FIB models are theoretical. There's a lot of work that's going into some of these things. Currently, the estimate is that the durability is similar. This is why we have done the work at City Deep, and we are following it closely to look at what is changing. You've got a high exposure to carbon dioxide in the area. You've got a high stress environment. And the last time I went there, which was last year, you still had the broom finish. Now, that broom finish was put on 13th of September, 2013. And that broom finish is still there now. Most concrete loses its broom finish within 6 months. So there are definitely some interesting aspects about the material and its durability. But to say anything else, I do not have a crystal ball. Even with concrete, we make certain assumptions, and those assumptions are rather large.
Right, noted.
I see Nicholas has put a question forward about the proper environmental analysis. Has it been done taking into account all the carbon contributions to the materials, including from the slag and fly ash? Yeah, all of these savings that we put on the project have taken the carbon contributions, not only of first derivative, but up to third derivative. So first derivative is direct carbon costs of the chemicals. Second is the transport derivative and other influences that those have had. And third are all the sundries that feed into those. So all of these carbon emission reductions have been looking at all three derivatives, Nicholas. I must say one other aspect. When you are using your 20 to 32% activator, your carbon emissions does not get massively reduced. You might have a 10 to 15% reduction, but it is not in the same realms as when you're using the activator in a proper chemical application, like what we do. Yeah, we don't use a sledgehammer to design our concrete. We actually do it in a lab. So, yeah, the application of those 30% activators really throw the whole green concrete out of the window aspect.
All right, any other questions? We'll start to round it up.
Willie, if I can just add one thing.
Yes, sir.
A lot of people are looking at, well, a lot of greenies are looking at alkali activation or geopolymer to be the saving grace in construction. The only problem is, even if you take all the waste materials, the metakaolins, which is not really a waste, but the slags, the ashes, and all of that available across the world, it will only be able to supply approximately 5% of current requirements of cement. So what you must remember is that alkali activation and geopolymerization is not the answer to let's stop cement and change to something else, because the actual availability is minuscule compared to what the requirements are.
Right. I think one thing, I'm just going through my notes now, one thing that struck me again was the water quality. And because you've got essentially an indefinite open time on your material and it's activated only through use of the activator, inconsistent water quality won't necessarily affect it as adversely as it would conventional concrete. Would that also be true for if you have organic compounds or something like that in the water that would traditionally push out your setting time and for your concrete?
Correct. As you see at Luriesfontein, there was a major issue with water quality. And if we had to use potable water, we would have to be transporting it from approximately 250 kilometers away. Now, when you have a construction job and you're transporting water for your concrete, 250 kilometers one way, that adds a massive cost. But through applying these technologies, you can get away with a water that's sitting at 15,000 parts per million sulfates, or material that have other things in them that are not good for Portland cement concretes. But these type of concretes can handle those type of issues. As I said, what we need to look at is all of these aspects. They're just another tool in the belt of a concrete technologist. It is not a replacement of. It is just to assist us to get a better material at the end of the day for our clients.
%. All right, guys, I have loaded Cyril's contact details into the chat. So you do have that if you want to type with him after the meeting. Cyril, thank you very much for your time today. Hanli, is there anything you would like to add before we close?
No, thank you, Valia. Just well done to the Western Cape branch for arranging this CONCRETEfix, but nothing else from my side.
Awesome. All right. Thank you, everyone. Thank you for joining us, and stay safe.